Okay, great. We are going to look at one example, how to prove that a transformation is canonical, and how to derive a generating function. And here is the transformation. It looks pretty messy, but let's see what we can make out of it. All right, first thing we need to do is prove that the transformation is canonical, and we know that we can do that using Poisson brackets. There are various notations for Poisson brackets, by the way, but I'm going to use square brackets. So I'm going to take the Poisson bracket of Q, BQ, and P. And as you very well know, this is dq, dq, dp, dp minus dp, dq, dq, dp. Which is obviously equal to 1. And that's what we should find. Remember that the Poisson bracket is an invariant with respect to coordinates if the transformation is canonical. So what we're actually going to do is prove that this transformation is canonical by calculating the Poisson bracket in the little q, little p variables. So that would be equal to dbq, d little q, times d big P, d little p, minus d big P, d little q, times d big Q, d little p. The first thing to do, well, I've already said the first thing to do, so the next thing to do is to calculate the derivatives. I'm actually not going to do it. We can put this in Mathematica and you can do them by hand. It just takes some minutes. I'm only going to write the results, and they're not difficult. But the q is derivative of the log is 1 over the argument, and then there is derivative of square root of q, which is q to the 1/2, so I get 1/2 of q to the minus 1/2. So putting the pieces together, I get that this derivative is the cosine of p, brackets maybe, divided by 2 square root of q times 1 plus, maybe using a square bracket here, 1 plus square root of q cosine of p. I'm going to drop the brackets shortly. Since I'm here, let me do the derivative. So we're looking at q. Let's do the derivative of q with respect to p. This one, same thing. We need the derivative of the log. That's going to give me the same function in the denominator. And then I'm going to do the derivative of cosine of p, which is minus sine p, so that this gives me minus the square root of q, the factor in front of the cosine of p stays, sine p over the argument of the log, which is 1 plus square root of q cosine p. Now for the derivatives of p, we don't have the log, And this is a little more messy, so this is actually 2 times q times sine of p cosine of p. Which is well, it's not too much work. Let's see how that turns out. I'm just looking at the result to make sure I don't make mistakes. Okay. Okay, so let me do it this way. I have 2 terms, the 2 square root of q times sine of p and the 2q times sine of p cosine of p. So the second one is going to give me, so I'm taking the derivative with respect to q, just going to give me the cosine of p times the sine of p. And the other piece, it's 2 square root of q times the sine of p. So a little more messy, but at the end that just gives me well, I can do it in more than one way. So let's see, let me write it this way. Sorry, I forgot a 2 here. That's the simplest way to do it. Sine of p over square root of q. Promise, I said I wouldn't do this when trying to do it in one step. So that's, I mean, I could collect the sine of p, but that's about the most compact form I can get this into. And the derivative of big P with respect to little p, I have the derivative with of this product, so the square root of the piece that only contains square root of q really doesn't, well, it does matter because it's got a sign, multiplies the sine of p. So I can do it piece by piece. I contain 2 square root of q times cosine of p. Sine of little p. And then I have 2q sine of p cosine of p, which is the sine of 2p. So that's going to give me the cosine of 2p. So that's going to give me plus 2q cosine of 2p, which may be more useful written as 2 square root of q cosine of p plus q cosine of 2p. Okay, so those are the derivatives, and then I plug them in here. A little bit of patience. Let's see what we get. Okay, so my Poisson bracket is going to be given by that combination of those functions. q p Poisson bracket is equal to square root of q. I'm just going to write the result. So I have cosine of p. As promised, I'm going to drop the brackets in sines and cosine divided by 2 square root of q 1 plus square root of q cosine of p, and that's dq dq, then dp multiplies 2 square root of q cosine of p plus q is sine of p cosine of p. Oops, no, sorry, wrote it backwards. I wrote the sine instead of the cosine. Let me leave it as cosine of 2p for one more step, and then I'll fix it. Then I have minus dq dp, which is got a minus sign, so it gives me a plus. Dp dq is 2 sine p cos p plus sine of p over square root of q times dq dp. I've already changed the sign, so we'll put a plus sign here so we're explicit. Square root of q sine of p over 1 plus square root of q cosine of p. Okay, a little bit of work, but at least we get this part, and we do get this part where this cancels this, and this becomes a square root. And then the denominator is the same. So we have cosine square of p plus the other piece with the cosine. So I have cosine of p that multiplies, so that's cosine square minus sine square. Cosine square of p minus sine square of p. Okay, that's all we have. And then the other piece gives me did I lose a square root? I did. Square root of q. Sorry about that. That's why I really didn't want to do this by hand, but you know. So here we have 2 square root of q sine square of p cosine of p. It's the first term. Second term gives me just sine square of p. And it's called no square root, okay? And then everything gets divided by 1 plus square root of q cosine of p. Almost there. Okay. I'm going to put these two together. They kind of look alike. I like them. So sine square plus cosine square. Here, what can we do? We can collect some p's, and we can collect square root of q cosine p, and then we have cosine square of p plus, oops, I mean, I do get plus, but let me do all the steps, minus, I'll make at least some steps, sine square of p plus 2 sine square of p, all divided by 1 plus square root of q cosine of p, and this gives me 1 plus square root of q cosine of p. You all see that this is 1. It's cosine square plus sine square. And in the denominator, I do have 1 plus square root of q cosine p, so it is equal to 1. Great. That's exactly what we were hoping to find. So we got the first part. The canonical, so if q and p are canonical variables and big Q and big P are canonical variables, so the Poisson bracket is the way we showed that this transformation was canonical. Could have done it with a symplectic form, taking derivatives, and be a nightmare. So that's one way to do it. Okay, then next we need to write this transformation in mixed variables. So, for instance, we need to solve one of the two equations for either little q or little p, and it's hopefully obvious which one's going to work. I'll leave you one moment to think about it, pause the video if it's not obvious. But with the first one, we can extract square root of, there is a square root of q, and there is a cosine of p. In general, dealing with the inverse trigonometric functions is not fun. Sometimes it happens. But the first equation is the one that looks more promising, and the one that's going to give us little q as a function of bq. So that is what we're going to try to do. And let's see what we find. So little q is going to be equal to, let's see. So I can take the exponential on both sides. I get e to the q is equal to 1 plus square root of q cosine of p. And from here, it's pretty straightforward. E to the bq minus 1 divided by cosine of p is equal to square root of q. So that q is equal to e to the q minus 1 divided by cosine of p squared. That's also the cosecant, not square. Did I get this right? But that's pretty relevant. Okay, so we got this part. Let me put a square around this. And then what we need to do is express this expression for p in terms of what we just found, well, we got an expression for square root of q. So that p, I just need to replace it, is going to be 2e to the q then there is the cosine denominator that gives me a tangent. There is the -1 that's going to kill the +1 in there. So that goes away. So I'm left with e to the q -1 times the tangent of p. Okay, now I have little q and big P as functions of big Q and little p. So I can find the generating function. Now you have to remember which one to use. So let me put it on the screen. Okay, since I copied this expression, maybe I shouldn't put it on the screen, but who cares? We see that what we have is little p and big Q. So that's going to be the third type of generating function. So let's get back to our example. Okay, so let me just write this down. We are looking for an f generating function of form f3, function of p, b, q, and t. And well, in this case, we're not going to have any time dependence, so who cares? Plus qi pi. In this case, we only have one variable. So I can dispense with the index. I'll just write the general expression. Qi is going to be minus df3 dp little pi, and big pi is going to be equal to minus df3 dqi. Okay. Now, yeah, got the signs correct. They're both negative. Now the differential of my f3 function of q and little p, or I use the other notation, sorry. Let me write it as function of little p and bq instead. So that's going to be equal, I'm taking the differential, so that's the f3 dbq dq plus the f3 d little p d little p, or from the expressions above, that's minus big P times dq minus little q times d little p. The expression for bq as function of so just write the expression that's going to be the differential of minus sign of e to the q minus 1 square. So writing the expression, the differential for q. Times tangent of p minus e to the q minus 1 square times the differential of the tangent of p. So the whole thing is the differential of e to the q minus 1 square tangent of p. So that's f. Or rather 3. E to the q minus 1 square times the tangent. Oh, not tp. And that's what we're trying to find. Now, I obviously skipped a step here, so I would encourage you to try to fill in the gap, what I didn't show you. But if you want to check what you're doing and confirm that what I wrote is correct, here's all there is to it. Minus PDQ is equal to the expression we have for P, which is this one. So it's minus 2e to the q e to the q minus 1 tangent of P in times dq. But this expression here is d over dq of e to the q minus 1 square. You can see it easily. You get derivative of a function of q square is twice the function times the derivative of what or the function itself, which is e to the q, and that's exactly what I come up there. And that's why this gives me minus tangent of p d. Maybe I could have written it this way, e to the q minus 1 squared. And the other piece you do exactly the same way, minus q dp piece we have there is the expression for q. Now, the expression for q I'm going to use is this one. So it's e to the q minus 1 square times 1 over cosine square of p times dp, but this is the derivative of the tangent of p plus or minus sign, so the whole thing is minus e to the q minus 1 square derivative of the tangent of p, or differential of the tangent of p. And putting the two together, we get the F3 expression we have above. I mean, that's where we were. Okay, and then may I lost a minus sign there. So sorry about that. All right, so that's how we can attack this type of problem. Of course, for each one, you'll have to figure out which transformation to use and how to get to it. But the general idea is it's the same. And if you thought that doing the Poisson bracket was complicated, keep in mind what the alternative was. So It maybe wasn't super easy, but it was a lot better than any other options that we have at our disposal. And I hope this is useful, and feel free to put questions in the or comments in the comments.